Okay, so the goal of this talk would be introducing some basic concept, starting from like very beginner level of how ROS work, and then also give you an insight on why ROS work in this way. And also briefly talk about gazebo simulation, particularly for ROS. We don't talk too much about gazebo. And then during the talk, there will be some commands that we frequently use, and hopefully it will be a good reference. And then we will skip the most complicated part about ROS and Gazebo, which is installation, compilation, and then set up the environment and all that. Those are the most frustrating parts about ROS and Gazebo. But I will talk about why we can try to skip that at the end of the talk. And also I will talk about how we use simulators for our multi-robot simulation for the recent work we have submitted to RTSS and also UPSLA. And there's something to note about that when you use simulation for evaluation, what do you need to be careful about? And so the structure of this work will be, first, I will talk about, this is based on some tutorials I found online. So we will talk about what constitute a robot application. What does a robot application based on ROS is in terms of how the code is structured, and then discuss what is the gazebo simulation job for a ROS-based application. And then there will be some demo on how a simulator, our multi-robot simulation is used in the UPSLA submission and the RTSS submission. The UPSLA submission is the Koord, which is conditionally accepted. And then this new RTSS submission is about unmanned aircraft system traffic management, which is more like in the urban environment, how do you ensure for example, the collision avoidance of like smaller aircrafts, like drones or fixed wing planes. Okay, so the first will be some basics about one, quote unquote, one ROS-based robot application. The quote unquote will be obvious later. So this is a example just from our CyPhyhouse project that how it quickly becomes complicated, as we can see. I'll first start by describing what are the hardware modules. So this F-110's car, it has a position sensor that is achieved by data wave positioning system. And then there is a LiDAR that is some Hokuyo model that can give you LiDAR scan. And then there is a actuator that when you send velocity commands, it will try to follow that velocity. In implementation, it's actually a Ackermann control command, but we'll skip the type here. So what is the simplest code structure if we want to just implement some controller on top of these three hardwares? So the simplest module would actually look like this, that you first need some library, and you need to import some package or library from the library provided by DataWave. And then there is probably this particular function telling you, okay, you can get the position of the car using this get position function. And then of course, Hokuyo LiDAR sensor similarly. And then for controlling, there is another hardware module that you can set the command, set the velocity as a command, and then you have some initialization code before, and then in your main while loop, you will try to get the position, and then you get the scan, and then you have some control, computing some control values of velocity based on your position, and then you have some scan. This one ignore the input. For example, you also have to consider if you have a target position, then this control should also consider that. But here we skip that. And then scan could probably tell you where are the obstacles, so your velocity also has to be adjusted. And then after you compute this, then you set the command, and then you sleep for some duration of time. So actually the in the implementation, actually you want to, this whole one iteration of this slip compute cost exactly d seconds rather than sleep d seconds after all the computation. So that is how usually the simplest robotic control loop would look like. And this if you look into some control system or control theory, then they will have this digital control loop, and then this is roughly maps the structure of a control loop where these are the sensors, and these the velocity is the actuator, and then you have this kind of a feedback loop. Okay, is this clear enough? Okay, but one problem with this simplest code structure is that your sampling of position and scan is bounded by this particular D period. So if you want to do something more advanced, for example, if the position comes in much faster than this D second, you probably have many samples. But because your main loop bounds, so you only read the latest position, then you cannot do something more advanced. And so a more common structure is actually look like this, that you actually have some shared variable here we call shared position, which is updated, and then in some other code segment, which is that you normally want to say something like, okay, when there is an event, such as, okay, hardware tells me there's a new position, then, for example, I can push the new position into some position history, and then we do some simple, like, for example, low pass filter to ignore, like, to try to filter out like noisy positions. And also you can have like some window or whatever, but those filtering will be done in a separate, let's say, thread within the same process, but in a different thread. So, and this shared position will be some shared variable between threads. And then in the main loop, you will just use the latest shared position. And the share scan will be similar. Okay, so this will be another like very common code structure you will look at in all the, even in ROS programs, it looks like this way. But what is the, so now I'm going to talk about what does ROS really improve on top of this very common code structure. So one thing, and these are like very technical engineering improvement rather than something very theoretical. So I hope everyone can get this and then know why ROS works in this way and why the complication of a lot of things ROS introduced. But, and ROS is only one solution. Maybe there are different solutions, but let's get into why ROS is, what ROS tries to solve. So there's some questions here that if today I changed the positioning system from Decawave to Vicon, which is exactly what happened in CyPhyhouse project. What do we have to do? The problem, then it will be like, okay, I actually need to import different libraries, and the different libraries, because they are different company, they have different names. So you have to go into, for example, go into the particulars, I don't know, the event triggering code, and then update everything. And then something might just happen that you change this, but you forgot to change this, or the type of things are kind of different. So you have to deal with the type of variables, things like that. And then, okay, and then the other thing is about reusability. So I probably also have this code for LiDAR scan, like doing some filtering, whatever. And now I don't want, I'm actually in CyPhyhouse, in the simulator, the same LiDARs can be used on drones as well. And it doesn't really change between whether it's installed on drone or installed on car, because they are basically the same model. It is not as different, like if you have, non-holo, sorry, the car dynamics may be very different from the drone dynamics, but the scan will be very similar. So how can I reuse the LiDAR code for drone as well? So this is another thing they try to address, that is trying to reuse as much code as possible. And then the third thing is actually quite common, that you just want some library that is for path planning, control, filtering, and it's not in this Python, but rather it's in C, C++, C, Java. And how do we really do that instead of reinventing the wheel in Python? So and the whole thing can be summarized as one sentence, is that actually it is because this controller code is tightly coupled with specific hardware design here, and then specifically only for Python. So what ROS proposed is just try to replace. I wouldn't say they want to just eliminate all the shared variables. No, it is more like replace some of the communication between data from using shared variables. Instead of using shared variables, they use message passing, because shared variables is tied to programming language, compiler, hardware, etc. And but even for message passing, there are many paradigms or patterns that is available. For example, you can do server client, and then this topic-based publish subscribe pattern. That is what ROS choose to use, because it decouples the knowledge about the source and the knowledge about destination. What it means is that the receiver, the recipient of the message, doesn't really care about who is sending the message, but rather, as long as the message represents the correct data type, correct information, which is the current position. So it doesn't matter whether it shouldn't matter whether you are using Decawave or Vicon or GPS for your positioning, but you only care about the topic of this message is the current position. So what ROS proposed is that this is like kind of the ROS APIs here, that these informations about position, LiDAR, and command velocity should be considered as topics. By the way, the graph is not really formally defined, so it might, sometimes the semantics of the graph might not match. But, and then, so this API tells you that, okay, I'm going to publish to this command velocity, and then I want to subscribe to position topics. and also subscribe to lighter topic. And then the position topic here, we have this position message callback, which is a mechanism so that whenever a message arrives, which is similar to what I was saying, that whenever a position is sampled by the hardware, I process the position messages. So in this way, it kind of decouples the hardware libraries from the controller here, where here you only import from ROS-PY, the ROS package, and then it only describes how the message is transferred through topics. And the rest, the gray part, is almost exactly the same. So the first question, it is how they address this. How do you switch between the DKW and Vicon? As long as you provide another, this will be a different code in a different package, probably nowhere near the controller, but it is just providing publish the correct position from the DKW hardware. And similarly, you can have another package for Vicon that is probably some different naming due to different companies. And then as long as they publish to the same topics, these two are decoupled from the controller. Yeah, so controller only has to import the ROS libraries for communications.
Oh. I have a question here.
Yes.
So I understand that the code in the center that you're showing is the controller code, mm-hmm. and we are getting to subscribe to this position topic.
Yes.
Now, so the person writing the controller code has to know that the name of the topic which has the position is called position.
Yes, that's one problem. Yes, that's, well, not problem, one feature.
Yeah, I'm not suggesting it's a problem, but basically, so how is that organized, right? So there are a bunch of different yes. devices who are potentially publishing the position,
yes,
like data
yes.
wave and GPS and whatnot.
Yes.
So how does the programmer for this controller know about these topics and what they're really supposed to be?
So I actually have some reaction about this design later on, but I can give you my answer now. ROS doesn't really have, for example, like static analysis or program analysis for helping you this. They kind of just say, you need to follow a naming convention and you need to know how to subscribe to the right positions. They suggest some best practice, but they don't really have a way to tell you or even to verify that you're subscribing to the topics correctly. So a lot of like the initial development overhead is on and like trying to figure out if you are publishing to and subscribing to the right positions of the right module that right node that is what publishing the messages.
Thank you.
Okay. Okay. So this is blocked. I think the similarly, as long as you have the subscriber, as long as you have the, sorry, this question was about how do we reuse the code for LiDAR for not only for the F1 car, F1 tank car, for the drones. Similarly, because we have this decoupling that this particular code for publishing LiDAR topics can be reused in the for drones rather than tightly coupled with the controller. So that's how ROS is able to address this two particular like practical engineering problems. So to simplify, well, like to simplify the the whole diagram. So each code or each process that's running the code can be considered as a node, which is defined. This is defined in the terminology used by ROS. They call this a node is a process that performs the computation, which is actually running the code. And then, so for our example, you actually you have like Vicon node, Descartes node, and as John just asked, if I have both Vicon and Descartes wave online, they probably all publish to the same positions. And this is allowed. It's a feature actually. And also you have a Hokkyo node for LiDAR, and then you also probably have a actuator node somewhere down the line to receive when it receives the velocity commands, it controls the car. And also this controller node, I forgot to include the input that it probably receives some waypoint from a higher level program that tells this controller node to do like position control. You go to this position. And so each node is exactly where the code is. And then each topic is, they call it named bus or channels for nodes to exchange messages. And in ROS, they also not only have the name of the topic, but also provide type or like the data structure of the messages. And yeah.
And the data structure is in which language?
The data structure is defined as a message format. So
so there's a language for ROS, message language.
Yes. So we can take a look on, for example, post. Yeah, this one. So this is how they defined a ROS messages. A post is supposed to represent a state of, for example, object or model, which includes position, which is in some point format, and then the orientation of the object. And then if you looking further, then the point is defined by some float, 3 float, X, Y, Z. And then for quaternion, they use the orientation. They use this quaternion system, which use 4 floats to uniquely define the orientation of the object.
And there is some translator, for example, from this format using some parser provided by ROS to Python and
yes,
plus and to every language.
So every language wants to support ROS, they will just have to support this particular message format if you want to use this message format. Yeah.
So you can't publish any type of message in ROS. You will have to abide with this constrained list of messages, right?
Yes, and also you can define your custom messages for the data structure you need.
And provide the translator as well for every language that you include.
So for C++ and Python, as long as you're using some of the, so if your complex type is based on some base type, then they automatically generate the code to parse the message in C++ and Python.
I see, okay.
Yeah. Okay. So for the for the ROS Computation Graph, I think it's simple enough. We already all know about this. So this is a simulation that I run a I just spun a drone, Hector Rock quadrotor, and doesn't do anything. But you can see this is, so the command is called RQT graph, if you guys can see it. And it will show all the nodes and the topics. And so for example, at the end of this, actually the command post is a position control command that directly sends to gazebo to control the drones inside the gazebo. And there are some other.
So gazebo is just another node?
Yes.
Okay.
So later I will I will talk about gazebo. So and then there are other commands you can do. If you don't have the GUI interface, you can do ROS topic list to get all the topics, and the ROS node list will give you all the nodes currently running in the ROS system. And of course, it's not only that. These two things would have like many subcommands for you to figure out everything. For example, in ROS topic, you can also publish using echo, or publish like one-off message to some topic you want to test about, and then echo will be showing, for example, let's see what the position is velocity x state. Oh, controller velocity x state. Yeah, so this is about the x dimension, and because it's not moving, so the value doesn't change much. So there are all these subcommands of all these useful command line messages, command line tools to help you figure out if you are publishing or subscribing to the correct topics. And it is very important to follow a naming convention if you are designing the ROS packages. And it's kind of emphasized in all the ROS tutorials and all. Okay, so kind of slow. So now so we started with the third question, that we also want some libraries that is not in Python that we are using. So because ROS has gained so much popularity that they have many bindings for different language. Currently, I know there are like besides C++ and Python, there are Lisp, Java, and C#, which covers a bunch of common programming languages. And because of this freedom, you can create intermediate node to use the topics with intermediate topics that do the computation you need. For example, in this case, you have position from both Vicon or Dekka waves. You probably want to do some sensor fusion or merging, or just merging the position from different positioning system might be implemented in this way. And your control node will be, but then your control node will be subscribing to a different topic. Okay, so this is like the solution proposed by ROS. And there, as I already mentioned many times, because you kind of try to divide and decompose modules into smaller and reusable packages, you kind of sometimes it is kind of difficult to keep track of how many dependencies you're using. And then also the building system, you need to get all the required dependencies. And sometimes you don't even know you have a dependency that is indirect or transitively depend on something. So the complex packaging and building system make it very difficult to install the packages as well as compiling the packages for beginners. And no, actually, even for me, it is sometimes. Like I think Ifan and I was trying to figure out this this particular package you want to install, and then we also face some problem about why it doesn't compile, what is missing. And the other thing is that this message passing actually introduce extra delays. So your timestamps on your, for example, sensor positions might be like, first might be imprecise, or second, when it is delivered to where your controller is, it is probably long enough to violate something. And then because you have this multi-processes instead of multi-threading, you cannot easily control the order of execution between processes as easy as threads. So as a result, there's really no real-time guarantees in ROS1, which it's a like huge topic in ROS2. They are trying to address that. How do you maintain this message passing style, but still try to achieve like real-time guarantees? And as far as I can see, it's very difficult because now you need a global scheduler for all the processes. And ROS also wants to be like cross machines. You can have some ROS node in one machine and some other ROS node in other machine. How do you even schedule in this case? Cross machines, that would be very difficult. So there, I have a link to a ROSCom talk that specifically talk about the real-time guarantees and the imprecisions that can happen in ROS1 system that, and then they talk about a lot of techniques to really ensure reduce delay, ensure real-time guarantees in real-time systems. But one of the things I think it's important is that maybe not all of the ROS nodes need to be time critical. So ROS can be used for non-time critical applications for sure. You probably, but if you want to use it for like medical device or something that is safety critical and with real-time constraints, maybe this is not the way to go. Anyway, but okay. So now going to talk about the gazebo simulation jobs for one robot application as we decided. So following what we have before that, you have a controller node, you have position, LiDAR, and all that. And then you have some waypoints from some upper level applications. This whole thing, up until this hardware, can be considered as one ROS applications that is really doing the control, like for example, position control. And from the perspective ROS, it doesn't really matter who is providing the position or LiDAR or command velocity. So you can have one giant node, like called SIM node, that provides this position and LiDAR and command velocity, which is exactly how we use Gazebo for ROS. So that's why I don't really look into Gazebo much. And we kind of treat Gazebo as a gray box or black box, which just provide positions, for example, at the right time. And the interesting thing is that you can also provide clock, the time, as a topic to ROS, and every node will follow the simulated clock. That's why, so you can simulate, you can mimic real physics with simulated clock. What does this provide us is that if your computer is really not as powerful, you cannot simulate 1 second of the real world in one, like CPU seconds, then you can use more CPU seconds to simulate one real world, one simulated second. Okay. So here I will go through everything very quickly. These are just technical details about this gazebo simulation. So for a gazebo simulation job, you will have a ROS robotic application you have, and then you want to construct a world, a simulated world. And the world that we care about is that first you have a simulated hardware, which they call it a model of the robot. And inside this model, it is actually describing what is the shape, the mass, frictions, collision, and all that. And then you have this initial state, which is the position, which includes XYZ position and orientation, and velocity includes XYZ velocity and angular velocity. And then there is this very tricky part that they need to have this sound plugin, something that publish to these topics, and these are the things that takes the most time to debug. But I'll go through it later briefly. And then inside the world you will have static models which doesn't move. It can be used to model terrain, floor map, obstacles, walls, buildings. And then there are some defining some physics. So a robot inside the gazebo world or a model basically have visual and collision. Visual is describing the visual shape of the model. With visual shape doesn't mean it has a real thing that you can collide to. So you can, and then there's another attribute that is really how do you model the collision between robots or robots against walls? So you can have visual without collision, which means this is something that only visible at the GUI interface or to the, for example, LiDAR sensors, but you cannot collide to. And you can also have invisible wall if you don't specify visual, but specify collision. And then, but normally they are aligned. You have a visual and collision for a particular part of your, for example, the wheel of the car. And then you have joints that to connect links, which is, for example, you connect the wheel of the car with the chassis of the car. And then you can specify like a range of degree for rotations, limits. There are many parameters, but these are something when you look into the gazebo model and then try to figure out, okay, what is wrong? These are something you can quickly look into. And finally, this plugin is something that is really difficult to debug, but it actually defines where the ROS topics is published or subscribed to. And this link will give you a list of existing gazebo plugins. They have predefined topics that for example, there are starting from the position, and also there are even for differential drive, Ackermann, and there are some plugin that supports, for example, Ackermann drive messages. But basically, it's very specific to each plugin, and it's where, if you are debugging, you need to really look into. And then for the gazebo world, I mentioned there are some physics. So they provide different physics simulation engines. And then they also provide some way to, like I just mentioned, you can use more CPU time, wall time to simulate one second in the world. And then there are models, which oh, okay, by the way, these angle brackets is the XML tags inside the files you can look into. So yeah, so on top of the robots I defined previously, there is also friend and pose, that is kind of important because their position is with respect to the friend of inference, and there is a tree of friends rooted from, for example, the global origin of the world, and then there are relative position of the car to the world, and then there are relative position of the link to the, for example, the wheel to the of the car. Oh, okay. So I'm not sure what happened. Do you guys still hear me okay?
Yeah, I hear you fine. I see the slides okay.
Okay, okay. And then there are more physics properties, like gravity, wind, light, which would affect the camera sensors and the LiDAR sensors as well. So these are how a world is really defined inside the XML. And there are much more. The thing you will look into is called the SDF format. There is a website defining the whole thing. SDF. They have they will explain all the text like I summarized here, and then if you are interested into really modify the model itself, then you will have to look into this specification and then modify some part of it. So for our simulation, we did do some modification so that, for example, reduce the bumping, the car doesn't make the car doesn't bump too much, or raise the angle of the camera or something. Then you will need to refer to this and then look into the particular tags to modify things. But these are, if you need it, you can look into it.
Hi, Chiao. So is this SDF, is it specific to Gazebo, or is it bigger than that? Like other tools also use it?
Tried to make it more general. I think right now still only Gazebo is the main community that is using this. I think they have something on the AutoCAD side that say they have the tool to export, for example, AutoCAD model into SDF format, but it's still a very specific to Gazebo, I think.
And this is what Chris was also talking about the other days. Like if you're using other 3D modeling tools like Unity, seems like there's a way to go at least back from Unity to SDF. So there exists some translators.
I think Yifan did look into some of the tools and our, yeah.
I tried a software called Blender before, but it seems like if the map is too large, it cannot successfully transfer the whole map into the SDF format. But like when I try to make some simple model in the Blender, like making several squares to make up a house, then I can transfer it into the SDF, and it can successfully load into the Gazebo. So I think there's maybe some requirements for the transformation from the Unity to the Gazebo.
Got it. Thanks.
Okay, so that was a quick review about Gazebo model. So the most important takeaway is that you need your job is actually a robot application, and then you have the initial state of the model, and then all the floor map or obstacles. And also you define some physics you want to simulate it, and you can define very weird physics. I've tried, but that's all. So what exactly does simulator give us? This is the simulation engine we developed inside the CyPhyhouse, inside the CyPhyhouse project. So basically what simulator is doing is to avoid naming collision. So if we have the position LiDAR command value the same, then you will publish two robots positioned into one topic, and you cannot distinguish them, and then you will confuse your controller. And also your controllers probably need to be named well. So basically what we try to do is just to separate topics and nodes with namespaces. And we do it for F110's car, and we do it for the draw model we have, a Hector quad rotor. The important takeaway is that it took Minha and I the whole summer 2018 to really figure out all the code that needs to be changed so that you can parameterize at the namespace in front of the topics. It is nothing difficult. It's just very laborious and cumbersome, and you just easily miss a lot of this lines of code.
Chiao, now your voice is breaking up for me. I don't know if your rest of you are also noticing this. Oh, okay. Something changed, and now your voice is. It feels almost like a mechanical thing with your headset or something. Anyway, so. Let's keep going. And the other thing is, a couple of us have a meeting at 2:30. So
yeah, sure. I think it will definitely finish before that.
Okay.
So takeaway is very important to follow a naming convention and make it easy to remap to different namespace. So there are two particular models inside the simulator we supported, which is the F110 race car by MIT, and then Hector quad rotor by TU Darmstadt from, I think, Germany. Yeah. And we have several gazebo worlds available, including the ECEB building and a kind of simplified version of the IRL and Intelligent Robotic Laboratory, the arena over there. And then we also have the device configuration for handling, for example, the namespace thing, choosing different planner, path planner in the middleware and all that. So I'll go quickly go through the two paper we submitted that use simulator for submission. So Koord is a language, I think, sorry, Ritika goes through this a few weeks ago, right? And I'll just quickly summarize that it's a simple programming language that use distributed shared memory and ROM-based synchronization to simplify how do you program distributed coordination programs. And then the main insight from that paper is that we want to separate what we call platform dependent and platform independent concerns. We will see it in a moment. And for example, the position control of cars or drones is very platform dependent because the cars may not turn may not do sharp turns, but the drones can fly like 3 different XYZ freely. But for deconflicting over paths or waypoints at this level of abstraction, actually the deconflicting shouldn't depend on the platform, whether it's cars or drones. You can just check if the path intersects with each other. And because we can separate these concerns, we can decompose how do you reason about the correctness. And in the paper, our suggestion is that the platform independent part can be almost automatically reasoned using program verification, symbolic executions, model checking, such kind of program verification techniques. And for the platform dependent part, there are more to discover, for example, using dry VR that was proposed in the paper. And from the perspective of this computation graph, actually, this looks like this, that this part so below certain topic, for example, waypoint topic, these topic below this, it's actually highly depend on the real device model, because your position control for the car versus for the drone is, I mean, just basically they're just different. But upon certain topics, if we have a good enough abstraction, the nodes here actually can be platform independent, and they can be used across different platform, different models, cars or drones. Doesn't matter. The heterogeneity shouldn't affect some nodes above some level of topics. And in the Koord semantics, we let the nodes communicate outside of ROS using message passing, because at that level we need to know precisely who is sending the whose position is where. So we know that we need the source of the message. So we have a middleware that help agents communicates outside of ROS to do deconfliction. So I can show the demo, but this is another, by the way, oh, sorry. Do we have time? We probably don't have time. So I'll just show the demo. This was I will just show the video. This was done last night. And this is the task application that the drones and cars are going to different test locations. And you can see that because the car and drone doesn't bump into each other, so they're behind the scenes that they don't collide to each other. But the drones will wouldn't bump into each other, and the cars will go for different test location concurrently. Okay, and then so that's how we use the Koord. We use some simulator for evaluating Koord, and kind of provide a proof of concept that Koord language can really work on different devices. And also it is actually deployed in IRL, but here in the simulator, we can deploy to much more cars and drones. I think the most we did was using like 4 or 5 cars, or 6 in total, 6 or 7 drones and cars. And for purely drones, we actually can do up to 16 drones for for shape formation. By the way, the demo, so these are the commands we just need to run that basically just start up the gazebo world and models and then run the experiment. These code are all at the GitHub. And I think Hussein and Hibran, and I think Ifan also used some of and then they already tried to use this Koord-based run Koord with the simulator already.
So
And
Chiao, here you showed us some pre-recorded video. If you were to run the live demo, can you hear me?
What?
Can you hear me okay?
What did you say?
I was just saying, here you showed us a pre-recorded video.
Yes.
If you were to run live demo, would it be a lot slower? Or what does it look like when you just run it? Oh, not segmentation fault.
Because of it would be a little bit slower because of the real-time factor. I set it to simulate 1 second in using like 2 or 3 seconds, because my computer is not as powerful as the server we have. But we can try it. So this is to spin up the gazebo world. Okay, 2 cars and 2 drones. And also because the copy the code. I need to copy the code here. So this is to run. This is to run a test scale location, but because I need markers. Okay. Yeah. So I hope the video streaming is good enough.
Yeah, this looks good. And I think when we are giving slightly longer talks in conferences or invited talks, or like the talk you're giving now, I think it's much more impactful to show a live video, live demo, and then we can switch to other videos. Yeah. No, this is not too bad. This is not too slow at all. Can it be sped up a little bit more with some tweaking? You don't have to do it now. I'm just asking.
I think, yeah, I don't know if you guys saw the message. I saw that the high CPU usage is slowing down the connection.
And here you can zoom in and change the perspective live, right?
Yes, yes. We can zoom in, we can rotate. And if you guys want, there are also some position information show on the side. Right now, and then if you guys can look at the button, it actually shows you how many simulated seconds already passed versus the real seconds. Okay, I think is this good enough? I think this is good enough.
Yeah, I got the idea. Yeah.
Yeah. Okay. Basically, it's mostly only 2 commands. First is to start the world, and then second is to run the ROS program. But there are some configuration we need to do, and then I didn't show you really how the Python code looks like. But everything can be found on the GitHub later. I think I have some modification on locally. I haven't pushed yet. Another work we have is the US traffic management system work we just submitted to RTS. We kind of formalized the traffic management problem as that each.
Hey, Chiao, let's save this for another time. You know, we have 5 minutes, and
okay.
I think this work is pretty interesting, and a lot happened in a brief amount of time. So let's not spoil it in like 3-4 minutes. Yeah.
Okay, so I guess the main difference between this work and the Koord with respect to ROS is that we have a central manager between communication between, but the same idea that we can separate things from platform dependent and platform independent, and then we reason about the platform independent part to show that the communication is good. And also similarly, we start up with the gazebo and then we run the script to test the protocol. So there's some ongoing work on the engineering side that we also try to port things into the AWS Robot Maker so that eventually we can have virtual machines in the cloud that with all the packages already precompiled, installed. So skip the installation, compilation, everything set up, all that. So the main work to be done is to make the simulator to work with AWS Robot Maker. And also Ifan is working on integrating another robot model that is a plane model. And this is what it looks like. Looks quite nice. So I guess we don't have enough time. I was hoping that we can discuss a little bit about some points we observed when we are really doing the evaluation using simulation. one thing is we were thinking about using gazebo simulation to collect traces so that we can use dry VR to reason with the play phone dependent part. But it actually takes quite a lot of manual work and also high overhead because we need to restart with specific initial states and all that. It can be done, but it's really slow and it's a lot of manual work. So that one idea we were talking about with Ritika is that if it is possible, you simulate a long trace, but the trace segments inside it can be reused in some way, so that you only run few simulation as in gazebos, but theoretically it actually means multiple traces for dry VR.